Hi, nitrous oxide, N2O, has long been called laughing gas and has had a use as anaesthetic, and its virtues for this application include being stable and unreactive. But it's no laughing matter. It's one of the key set of greenhouse gases, as showing in the slide, as the broccoli. As we shall see, its story is something of the reverse of the properties of ozone. Its reactivity is much less than ozone, and its impact is thought more to be as a greenhouse gas than having an effect on the absorption of high-energy UV in the stratosphere. But it does have some similarities to the fluorinated gases. Unlike the fluorinated ozone depleters, nitrous oxide has a long-standing natural base level above the part per trillion level. For comparison, the parallel figures for methane are also given. The baseline concentration is lower for N2O than methane, as has been the increase in recent years. These graphs have been used in other videos to show the energy bands of the radiation coming from the surface of the Earth. An absorption by CO2 sits over these curves, and the molecular motion causing this is its bending. So it's not surprising that the fellow linear molecule N2O has a similar effect, albeit at a slightly lower frequency range. But N2O differs from CO2 in not having a centre of symmetry, and as a result there is an additional vibration that is infrared active and also absorbs around this critical energy range of the Earth's emission. This and the long lifetime in the atmosphere renders each nitrous oxide molecule to have a substantially higher global warming potential than carbon dioxide and indeed methane. From the pre-industrial baseline of 270 parts per billion, the atmospheric concentration has grown to around 334 ppb, a rise of 24%. The annual emissions have also increased, but the slopes have reduced over what it was 10 years ago. Emissions from industrial sources have been reduced. We can see that the relative magnitude of source types is very different from CO2 and N2O. Energy and agriculture have swapped around, with nitrous oxide emissions being strongly linked to agriculture, land use, and emissions from waste. In large measure, this can be explained by these extracts from the global nitrogen cycle. In pre-industrial times, it is estimated that atmospheric nitrogen gas, which is fixed into the soil by natural enzymes called nitrogenasers, fixed as ammonia in equilibrium with its acid form ammonium, was to a level of about 200 million tonnes per year. This is thought of reduced to about 150 million tonnes by 2017, but this reduction is far outweighed by the use of fertilisers, of which 119 million tonnes were nitrogen-based in 2018. In aerobic conditions, the ammonia-ammonium pairing, NH3, NH4+, is oxidized to nitrite, NO2-, and nitrate, NO3-, and all of these are very soluble water-soluble components, and much is washed into the watercourses. And a portion of this is also converted to nitrous oxide, and this is the predominant cause of the increase in the emissions in recent decades, and thus enhancing the greenhouse effect. However, this is not the end of the story. Here I am reusing a diagram from the videos about ozone and CFCs to illustrate the basis of the protective ozone layer in the stratosphere. Ozone, O3, absorbs high-energy ultraviolet light that might otherwise cause chemical change in mine and your skin, one potential result being skin cancer. The effect of the absorbing of the light is to split the ozone molecule into an oxygen 1, O2, and an oxygen atom, Both are then in excited states and very reactive. In a similar vein, this other triatomic molecule, N2O, also splits when exposed to ultraviolet light into an oxygen atom and the nitrogen molecule, N2, which is a harmless bystander. Nitrous oxide also reacts with the excited oxygen atom, and that results in the generation of two molecules of nitric oxide, NO. An intrinsic byproduct of nitrous oxide hanging around in the atmosphere for quite a long time is it migrates up the atmospheric column and adds to the pool of nitric oxide in the stratosphere. How much depends on the temperature of the stratosphere, which in turn is affected by the changes in the lower atmosphere. Nitric oxide can abstract an oxygen atom from ozone to form an oxygen molecule and nitrogen dioxide, NO2. NO2 itself will react with an oxygen atom to create another oxygen molecule and reform nitric oxide. So just like chlorine atoms coming from the decomposition of CFCs, nitric oxide catalyzes the decomposition of ozone in the stratosphere. We may be used to thinking about the problems caused by excess nitrogen-based fertilizers, ammonia or nitrate-based, as distorting the ecology of water systems. But we can see that the release of the attendant nitrous oxide also contributes significantly to global warming, and on top of that, the nitrogen oxide formed in the stratosphere is now one of the major causes of the depletion of the ozone layer. Laughing gas then definitely is no laughing matter, and worldwide patterns of our industrial agriculture have to be much more refined to remove these problems.